was going to talk about that first today. So this is our definition of what it means for an ideal to be generated, or what's the ideal generated by the set A. So what it is just collect every ideal that contains A as a set and intersect them all, right? We know from last time that the intersection of ideals is still an ideal. So when you intersect every ideal that contains A as a set, then what you get is the smallest ideal that contains A as a set. Now, in practice, if you're sitting down with a pencil and piece of paper, if you're the working mathematician, you're probably not going to go collect every ideal and start intersecting, right? So let me give you this example remark. So I'm going to go from yeah. So in general, if R this is commutative identity, then so what do the elements in RA look like? Well, there's the workaday kind of thing. If I just give you this random set, and here I'm going to assume that it's not the empty set, because we already talked about the fact that the empty set, the ideal generated by the empty set is just the zero item. But we're going to assume for the purposes here that A actually has some stuff in it. The ideal generated by A is just all linear combinations from RI AI, where the RIs are in here, the AIs are in here. Notice that this is a vacuum cleaner, because if I multiply any sum of this form times something in R, I still get something of this form, right? Now, if I start relaxing it, if R is not, so this is the easiest thing, right? I love this form because all the ideal generated by A is just all linear combinations, R linear combinations of stuff that's in A. That's pretty easy, I think, to write yourself. What happens if R is not? Well, now we start going down the rabbit hole. We start talking about left ideals, right ideals, two sides. RA is this is the left ideal generated by A. And here it's only a left ideal. And RA it looks like the same form here. This is again a subgroup. This is closed under addition, because if I have two sums of this form and I add them up, I just get a bigger sum of that form. It's just got potentially more terms, right? Notice that this is a left ideal, because if I multiply on the left, multiply on the left by some R, this is just the sum of R or I, AI, which is still an RA. Everybody okay with it? but there's no guarantee that multiplying from the right side with R is going to, because that'll give me RIAIR, right? And that's not necessarily this form. So this, the right ideal, generated by A. What do you suppose elements of this will look like? Exactly. Well, summation, where now I have the AIs on the other side. Now this is also a subgroup, but this time it sucks in from the right, but not necessarily from the left this time. Maybe I don't like right and left ideals. Maybe I want ideals, period. How am I going to solve that? What's the ideal generated by A going to look like if I want it in the non-commutative case? If I want it to be left and right. Oh, I think you're on the RA. That's essentially it. Generated by A. Set of things like this. RIAISI, or RI plus I. All right. So now, again, this forms a subgroup, but now I've sort of got it protected on both sides. So this now sucks in from the left and commutative is worse, right? Or not commutative. Commutative was easy, right? Oh, I love the commutative, right? It's just this. It sucks from both sides because the ring is commutative, et cetera, right? Okay, and now I've got to worry about left and right. But this is the ideal generated by A from both sides. The work of a person. It's just all linear combinations. Every possible R on this side, S elements of R bookends, and A is the creamy middle of the Oreo, right? It gets worse, right, when I remove commutativity. Yes.
Does it matter that this one may or may not have identity as well?
Okay, I'm getting to that. As bad as it, I'm assuming that it has identity all the way through so far. If I remove identity, it's much worse, believe it or not. So let's just think about what a typical element has to be if I just take a single element. So this is why this little subtopic can be called why Jim likes commutative rings with identity. If R is general, not necessarily commutative, or with identity, then what is the ideal generated by A look like? Where A and R is a single element. This is sometimes called the principal idea. I don't have just a general set. I've just got a single element. I want to, so I'm asking myself, I take an element out of R. What does a typical element of the ideal generate of this? So the intersection of all ideals that contain this. Well, So I'm gonna try to learn this. Certainly, you might have elements of this form. Here, Ri prime, or R, I'll add this as I go along. Is that gonna be good enough? Or not?
Kind of.
You also have to throw in elements of this form. Right? But you said, but Jim, didn't you cover that here? Well, no, I didn't, because this assumes that you can have one of these Ri prime be one. And if there is no one, the ideal contains A, and if it's gonna be a vacuum, it has to contain A multiplied by stuff from R on the left. By the same token, what else do you have to have? You also have to absorb it from the right. Notice, I don't need a sum here, because if I have T1A plus T3A, I can group that as T1 plus T3 times A, right? So sums of these will all collapse to a small one. So that's economical. So, all right, so when I multiply this on the left by some R, this is absorbed, and this thing goes into here. If I multiply this on the right, then it's absorbed here, this goes into here, and it's absorbed in this form, right? But that's not all. There are still other ways. Let me point out something. The ideal generated by A should contain A. I think we could all agree with that. There's no guarantee that A can be any of these terms because I don't have an identity. Right? So there's no A there at all. Right? If there's no identity, none of these might be A. So now you've got to additively join in A as well, right? Because there is no one. Here, you might say, well, what if n is one? That one is not necessarily the ring. That just means put A there once. So this is what a general element of the ideal generated by A looks like if you can't assume commutativity or has identity, right? This is an unholy mess, right? Whereas if R is commutative with identity, the ideal generated by A is just a set of elements of the form RA. Since there's only one element, you don't even need to write a sum. Let's see. Okay, any questions?
That's the line. Hey, related to R or is it just?
No. These are completely arbitrary elements of R.
Okay.
Yes.
You say that this, all elements in. What's it called? Forgot the name. In the thing generated by A are,
Ideal generated.
they look like that. That doesn't necessarily mean that that notation right there is all elements, right? Or does it?
This
Okay,
notation
and all
means
elements.
this is the ideal generated by A.
Okay.
And what it actually is a set is every multiple of A. That's it, right? You don't need the sums earlier because if you have R1A, if you have R1A plus R2A plus R3A, you group that together, it's a single something times A.
And this only works for left ideals because it only sums in.
Oh, no, this is both ideals because I'm
Okay.
assuming it's commutative, right? Yes.
What exactly does it mean to have an ideal generated by A versus like an ideal of R?
An ideal of R is just any ideal that satisfies, it's a subring that's a vacuum cleaner. The ideal generated by A is that particular ideal that's the intersection of all ideals that contain A. But here we've written it in a very simple form for a commutative ring with identity, a very ugly form for a more general ring. All right, but that is just, it is just the ideal generated by A. It's the smallest ideal in the ring that contains the element A in this particular case. So this is the last thing that I went over. I'm going to skip the proof of one because we actually did this essentially earlier when we first talked about it. We talked about, oh, an ideal is proper. If you have a ring with identity, the ideal is proper if and only if it doesn't contain one. And that's essentially what that first statement is. Well, let's prove the second statement. Proof of two. Suppose R is a field. Oh, this direction. Suppose R is. Okay. What does it mean to be a field? It means that every non-zero element is. Well, so the non-zero elements are grouped under multiplication. So every non-zero element is invertible, correct? Okay, so I in R being I want it to be proper. Let X be an I. I know that it, ideals are not empty, so I know that there is one in there. If X is not zero, then since X inverse is in R, because all non-zero elements have an inverse, this implies X inverse times X, which is 1, is in I. So I equals R by part 1. And this is a contradiction. So I 0. Because what we proved here is that there is no non-zero element in this idea. So there you go. If R is a field, 0 is the only proper ideal. And let me recall for you, just to make sure that when I say the word proper for an ideal, I mean an ideal that is not the entire ring. It's strictly contained in there. Let's do the other direction. Let's suppose that 0 is the only proper ideal. I want to show that R is a field. So what I want to do is I want to show that every non-zero element of R is invertible. So let's select a non-zero element of R. Consider the ideal generated by X. Right? Now, of course, so notice our assumption is 0 is the only proper ideal. And since X is a non-zero element of this, right? The ideal generated by X must be all of R. Because the only proper ideal is 0, and the ideal generated by X has X in it, which is not 0. So the ideal generated by X must be all of R. So 1 is in the ideal generated by X. Therefore, 1 by one, we have the X, well, no, I'm. I'll go through. So one was, since the ring has one has to be an element of X. So there exists R in R such that R is. For the typical element, the ideal generated by X is just R times X. Therefore, X is a unit of R. So R from any non-zero element X has an inverse. Okay. Okay. Get a definition now. This is actually, this definition, these definitions, I should say, are central. They're central concepts in ring theory, especially commutative rings with identity. Definition 936. See. Number one, an ideal M in R is maximal. And I want to reemphasize this here. It's maximal if M is proper. I don't want it to be the whole ring. That's cheating. And if N is an ideal such that then N equals M. What it means to be a maximal ideal is you cannot, it is a proper ideal, so it's not the whole ring, and you can't squeeze any new ideal between it and the ring, right? So M is contained in the ring, and if you try to jam something in between there, it's either got to be M itself or it's got to be R. So it's maximal if nothing fits between it and the ring. There's a related concept, it may not look like related, but we'll kind of explore that a bit. Two, an ideal P, again strictly contained in R, is prime if P is proper. Again, it has to be a ideal that's strictly contained in the ring, and if A and B are ideals of R, with P containing AB, then P contains A or B. What needs to be applied is if it contains the product of two ideals, it has to contain one of them. Okay, so let me ask you all this. How many of you, somebody give me, what's your favorite definition of a prime element? What does it mean for something to be prime?
Prime order.
What's it? It's
Prime order.
no, I'm talking about like a divisibility property in the integer. Yes.
Composite.
Okay, not composite. That's a very common definition. It's only divisors are itself in one, but it's not one, right? That only works for UFD stuff. Is there another definition you might have heard?
Can you tell me what UFD means real quick?
It means that you have the fundamental theorem of arithmetic, that
Oh.
everything factors uniquely into primes. How many of you have ever heard this definition? An element is prime if P divides AB plus P divides A. How many of you have ever heard this definition of a prime? This is really the correct definition of a prime. Notice the similarity to this, right? That one says P divides AB, this says P contains AB. Means that P divides A or P divides B means P contains or P contains. The notions of containment in ideals is very closely related to the notion of divisibility in elements. Yes.
This is kind of a smart aleck question. Is that like an exclusive or?
No.
No, okay.
Okay, so let's look at some examples here. Want help with the homework, right? Can anybody give an example of an ideal in the integers that is maximal? Somebody remind me what the ideals look like in the integers.
Maximal.
Oh, well, so here's, let me give you an example. 12. If you look at the ideal generated by 12, this is all multiples of 12. Is there something bigger than that ideal that I can squeeze between that and all the integers? How about multiples of 6? The ideal generated by 6 contains that. So that was not quite maximum. Yeah. Any ideas for a maximal ideal?
You said what you just said, because you were saying, can you say what you just said again? Because you're giving it.
The ideal generated by 12, for example, is not max because it is properly contained in the ideal generated by 6, which is properly contained in Z. So I can squeeze something in between that and the integers.
So it would have to be generated by, or like a prime number?
That might work. How about this? Right? This ideal is maxed. I think we can all agree that it's proper because one's not in there. Right? Now, suppose there's another. Suppose there's another ideal between 2Z and Z. What do I know about I? I know that I is equal to NZ. Because we know that every ideal of the integers, we talked about this last time, is form NZ, where n is a natural number of 0. Agreed? Well, notice that 2Z is contained in NZ. Therefore, 2 is an element of NZ. Because 2 is in here, so it's in here. So, 2 is divisible by n. Now, pray tell, what are the divisors of 2? One and 2. So this is textbook maximum, because if n is 2, you got equality here, and if n is 1, you have equality. Right. So that's a maximal ideal, and your generalization is correct.
put P in the proof and it works.
Yeah, there's nothing special about two other than the fact that it's prime. Right? Notice that two is also a prime item. Suppose I'm gonna simplify this a little bit because I know that A is equal to NC and B is equal to MC. Here in M are in the natural numbers UBC. This means that 2Z contains NC MC, which it's not difficult to show is NMZ. So in M, this is the same trick I used before. NM lives here, so it lives here. Therefore, 2 divides N. But 2 is a prime number, right? So 2 divides N, or 2 divides N. And in the first case, this means that 2Z contains NZ, or 2Z contains MZ. So 2Z contains A or 2Z contains B. So this is a prime ideal as well. We are going to discuss the rich structure of these. But first I'm going to give you one more definition. And then I'm going to give you a theorem here. Any questions so far? Let me give you another definition to go with this, and then I'm going to put it up there with the prime ideals. This is, as you will see, a one. And this is the context in which I'm going to look at primes, maximals, and radicals the most. And I and R an ideal. We define the radical of I and sometimes it's written rad I. This is the set of X in R such that X to the N is in I. And in the natural numbers also. And we say that I radical if so another way to think of this is radical if X and I implies X is in. Now, let me point out a couple of things about this. The first is every time I do it. Well, actually, let me get this. Number one. This may not be clear, right? Because I give you this definition here, radical lie. This is just select all the X and R, so some power of it lands by. Right? It might not be clear that this is an ideal, right? Huh. Let's prove this. So my notation here is, I'm gonna let X and Y be in the radical of I and R and R. Okay, so this is actually going to be very similar to something you've seen before. What does it mean for X to be in the radical of I? It means a power of it is in I. Agree? So what does it mean for Y to be in the radical of I? It means a power of Y is in I. Maybe not the same one. Now here's the tricky part. And notice that of course 0 is in I, right? In fact, everything in I is already in the radical of I because that to the first power is I, right? Okay, I'm going to take this apart bit by bit. Let's use the subgroup criteria. We know the 0 is in I, so it's not the empty set. Anybody want to guess? It is. There is a big enough power. Anybody want to guess what the power is that I need for this to be in I? Or that guarantees it? Consider X minus Y to the N plus M minus 1. I think that'll work for us. And this is X to the K. Actually, I'm going to do X to the N plus M, N plus M minus 1 minus K, Y to K, and N plus M minus 1, choose K, K. The minus 1 of the K just handles the negative that flops up every now and then with the Y. All this binomial coefficient stuff doesn't really matter. What's really going to matter is this. Notice that if, let's see, what was it for Y? M. If K is greater than or equal to M, then Y to the K is in I. Everybody agree with that? Because Y to the M lands in I, and so every successive power after that will keep getting sucked into the I to the I. Everybody cool with that? So all terms for K greater than or equal to M above are in I. What about the ones below it? What if on the other hand, K is less than or equal to M minus 1? Well, then this implies N plus K is less than or equal to N plus M minus 1. And I'm going to bring that K over the other side. So x to the n plus m minus 1 minus k is in I. Because now the power on x for k less than or equal to m minus 1, the power on x here, this n plus m minus 1 minus k, exceeds n, which is what it takes to get into I. For k less than or equal to n minus 1, all terms. So radical I, and that's really the heavy lifting for the ideal business, because it's easier to prove this vacuum. Also, note, for all R and R, Rx to the n equals R to the n x to the n, which is I. So radical I is an ideal. Because since x is in the radical ideal, Rx is also in the radical I. Okay, so the radical of I is back to my ideal. Let me also make the following observation, and that is any prime ideal is radical. The converse is not true. So also note if I prime but before I do this, I'm going to prove following little lemma to help us out. Proposition. Let's suppose that R is commutative with identity. Proposition 937. It's E in R is prime. If and only if A, B, and P implies A is in B by A is in B. This is one of the coolest characterizations of prime that I know, and that is the product of two things being in the ideal means that one of those two has to be. Okay, so let's prove this one. This is a lot easier in practice to use than kind of the clunky one about, so the actual definition of prime, where if P contains the product of two ideals, it has to contain one of the two ideals. If you're in the case of commutative ring with one, this is easier. Because to test if it's prime, just if any product of two elements is in the prime, if one of them's in there, that's what it means. Proof. Suppose this is prime. Well, this certainly means that the ideal generated by A, which is the ideal generated by A times the ideal generated by B, is contained in P. Because the element AB itself is in P. Since P is prime, P contains A or P contains B. But of course, A is in this ideal, B is in this ideal. Hence, A is contained in P or B is contained. How about the other? How about the other direction? Right. So suppose so we started with PB prime here. Now suppose that suppose we have A, B, P plus A's and B. Okay, so we have to show that it's prime. Now, the ideal P contains A, B. Then let's suppose that B is not contained. We need to show that A is contained. So we're going to assume that P contains this product AB, and we're going to assume that B is not contained in P. We're going to show that A does contain. Since P does not contain B, there exists B in B such that B is not in P, right? So that is, there has to be something in B that's not in P, otherwise P would contain B. Notice that for all A in A times little b is in AB, which is contained in P by assumption. But as B is not in P, because we're assuming B is not in P, and AB is in P, this implies that A is in P. And this holds true for all A in A. Because A was any element of A times B is in AB, so it's in P. B is not in P, so A must be. So A is contained in B. And so P is B. I will leave you with the following observation that I promised earlier. And this is kind of the way to do it. Claim if P prime so let's suppose x to the n is in P. And suppose n is minimal, such that x to n is in P. Everybody okay with it? So x to the n is in P, and we'll assume that that's the smallest power. Note that x to the n is x times x to the n minus 1. We'll say this is minimal in the natural numbers, such that this is true. Since P is prime, X is in P, or X to the N minus one is in P. But N minus one is less than N. So X is in P by minimality. So, right. Okay, any questions on that? Any questions? Okay, don't forget the review session, this afternoon at 5. I hope to see you all there.